In this video, we're going to talk about how to calculate the isoelectric point of an amino acid. So let's use glycine as an example. So glycine has a chirocarbon with 2 hydrogen atoms, a carboxylic acid functional group, and an amino group. The pKa of the carboxylic acid functional group is about 2.3, and for the amino group, it's 9.6. So with this information, calculate the isoelectric point of this amino acid. So the first thing we're going to do is create a number line. And we're going to put the pKa values on this number line. Now our next step is to draw the dominant forms of the amino acid in each of these 3 sections of the number line. So at a pH of less than 2.3, the amino acid will be fully protonated. So the amino group will have a positive charge, and the carboxylic acid group is already protonated. So this is going to be the dominant form at a pH that's less than 2.3. Now, when the pH goes past 2.3, the carboxylic acid functional group will lose a hydrogen. So the dominant form will look like this. The nitrogen will still have a positive charge, but the oxygen of the carboxylic acid functional group now has a negative charge. Now, when the pH goes past 9.6, the amino group will lose a hydrogen. So it's going to be deprotonated, and this will now be the dominant form of the amino acid. So on the left, the net charge is +1. In the middle, it's 0. And on the right, the net charge is -1. Now, to calculate the pI, we need to determine the pH of the Zwitterion. Which of these structures represent the Zwitterion? Would you say it's structure A, structure B, or structure C? The Zwitterion is electrically neutral. It doesn't migrate in the presence of an electric field. It has both a positive and the negative charge. So structure B is the Zwitterion. Now, in order to calculate the pI, we need to take the average of the pKa values to the left and to the right of the Zwitterion. So to the left of the Zwitterion, the pKa value, or pKa1, is 2.3, and to the right of it, it's 9.6. So it's going to be 2.3 plus 9.6 divided by 2. So that's going to be 2 plus 9 is 11, 0.6 plus 0.3, that's 9. So it's 11.9 divided by 2. 11.9 divided by 2 is about 5.95. So that would be the isoelectric point of this particular amino acid. So at a pH of 5.95, the dominant form of the amino acid will be almost completely the Zwitterion. Now let's work on another example for the sake of practice. So here is another amino acid. Like all amino acids, it has a carboxylic acid functional group, an amino group, a hydrogen atom, and the R group is going to look like this. So what type of amino acid do we have? Would you say this is a polar amino acid, nonpolar, acidic, basic, aromatic? This is lysine. And because we have an amino group as the R group, it's going to be a basic amino acid. Now, the pKa values for lysine are 2.18 for the carboxylic acid functional group, 8.95 for the amino group, and 10.5 for the amine on the side chain on the R group. So using these 3 values, go ahead and calculate the isoelectric point of the Zwitterion for this amino acid. Feel free to pause the video and work on it. So let's create a number line. And let's put the pKa values. So here this is going to be 2.18. The second pKa value is 8.95. And the third one, 10.5. Now let's draw each of the 4 forms of lysine. So when the pH is less than 2.18, this amino acid will be fully protonated. Each nitrogen atom will have a positive charge. So this will be the dominant form of lysine at a pH below 2.18. Now, at a pH between 2.18 and 8.95, since we're going past this pKa, the carboxylic acid is going to lose the hydrogen. And so the structure that we're going to get is going to look like this. Each nitrogen atom will still have a positive charge, but now the carboxylic acid functional group is deprotonated, so it carries a negative charge. We have a carboxylate group now. Now once we go past a pH of 8.95, the nitrogen group here will lose a proton. So instead of being H3N, it's going to be H2N. And so we have this structure. And then finally, at a pH beyond 10.5, the last nitrogen at the top will lose its proton. So now we could determine the net charge of the amino acids. So on the left, we can see that the charge is positive 2, because there's a plus and a plus. The next one, it's plus 2 minus 1, so that's positive 1. And it's always going to decrease by 1 from here on. So this is plus 1 and minus 1, that's 0. And for the last one, we can see that it's negative 1. So this right here is a Zwitterion because the total charge is 0. We have a positive charge and the negative charge. So to calculate the isoelectric point of the Zwitterion, we need to average these two pKa values. So it's going to be 8.95 plus 10.5 divided by 2. So 8.95 plus 10.5, that's 19.45 divided by 2. This gives us an isoelectric point of 9.725. So you could say it's approximately 9.7. So that's how you could determine the isoelectric point of an amino acid. Now, for the sake of practice, let's work on one more example. So the amino acid under consideration is called tyrosine. It has an aromatic ring with a hydroxyl group attached to it. The pKa of the carboxylic acid is about 2.2. For the amino group, it's 9.1. Now, for the hydroxyl group, most phenol groups have a pKa of 10. Some textbooks says that this is 10.5, 10.9, 10. It's somewhere around 10, but for the sake of simplicity, let's say it's 10.5. So using this information, calculate the isoelectric point of tyrosine. So let's begin with a number line. So we're going to have 2.2, 9.1, and 10.5. So there's 4 structures to draw. 1, 2, 3, 4. So starting with the first one, everything is going to be protonated. The amino group will have a positive charge. The carboxylic acid will have its hydrogen, and the same is true for the phenol group. So that's going to be the structure at a pH below 2.2. Now once we go past 2.2, the carboxylic acid is going to lose a proton. And so we're going to get this structure. So here we have a negative charge, and here we have a positive charge. Now past 9.1, the amino group is going to lose a proton. So it's going to be H2N instead of H3N+. And then finally, once we go past 10.5, the hydroxyl group is going to lose a proton. So the total charge is +1 for the first structure, and then it's going to be 0 for the second one, -1 for the third, -2 for the fourth. So it always decreases by 1 from left to right, as you can see. The Zwitter ion that we're looking for has a net charge of 0, so this is it. So now that we've identified the Zwitter ion, we need to take the average of these two pKa values. So the isoelectric point is going to be 2.2 plus 9.1 divided by 2. So that's 11.3 divided by 2. And that works out to be approximately 5.65. So that would be the isoelectric point of tyrosine. So that's it for this video. Now you know how to calculate the isoelectric point of Zwitter ions for amino acids.